Okay, today we're going to be making some op-amp circuits for Unit 35 devices and circuits. So we start off by adding an op-amp, then go to the settings and I'll change the symbol so that it has the inverting input on the top. Click and get a ground for the non-inverting input. We're going to make a inverting amplifier first. So then we get a resistor, and I'll change the symbol to the more modern symbol. Duplicate it for the feedback resistor. Remember, the gain is minus RF over Rin, or R2 over R1 as it shows at the moment. I'll get rid of the net labels, although you don't need to. So then wire up the inverting amplifier. You could use a 741 op-amp, is quite a common one. Then we need an AC voltage, which will give us a sine wave. We put that into the inverting input, and of course ground the other side of the supply. You don't need to turn off net labels. So we'll add a voltage probe on the input, which I'll change the name to Vin. Put another probe in blue, this trace will be on the output, and I'll call it Vout. If you double click the AC generator, you can change the peak voltage and the frequency, but I'm going to keep it 1 kHz. At the moment the gain is R2 over R1, which is 1 over 1, so it'll have a gain of 1 at the moment, but it'll turn it upside down. It'll invert it, hence the minus RF over Rin. So I'll change the resistor, feedback resistor to RF, input resistor to Rin, click simulate, and that's the real-time simulation there. If you click on split, you can see the graph and the schematic at the same time. You need to click pause when you're on the grapher in order to stop the simulation, or to pause it rather than stopping it. And then scroll down. If you zoom all, it shows you all that's been simulated so far. And here on the x-axis, the time axis, you can change it to say 20 milliseconds will give you that much. But we want to zoom in usually, so say 5 milliseconds at 1 kHz. If you want to change the gain to 2, as in minus 2, you need to change your feedback resistor to twice as big as the input resistor. (2K over 1K) will give us a gain of minus 2. Remember to pause the simulation when you're changing the time base and that. You can add cursors. I've got y-axis cursors which will come across the screen. I'm going to make sure I've got V-in and V-out. So we can see our V-out in blue at 2 volts and V-in is at 1 volt there. You can also export the schematic image and grapher images. Remember to save your file so that you can use it again. Secondly, which we can use in Unit 35 devices, P4 is a non-inverting op-amp, and all we're really doing here is changing the order of the inputs. So we're going to put our sine wave into the non-inverting input of the op-amp, the one with the plus sign, and then we'll put our ground on the inverted input. Don't forget to change where you put the input voltage probe. So this is now a non-inverting op-amp with a gain of 1 plus RF over Rin. So RF over Rin here is 2 over 1, so it's a gain of 3. If you look at the cursors, it shows you what the voltages are in the bottom left. And the change in voltage with the dy part. You can turn cursors off and just hover over the waveform to see the voltage levels. I'm going to save that one as a non-inverting amplifier. The gain is 1 plus RF over Rin, and in my case that equals 1 plus 2 over 1, which is 1 plus 2, which equals a gain of 3, but it's not inverted in this configuration. Another op-amp circuit that we can create is called a Schmitt Trigger. So I created a new file, click on a 3-terminal op-amp, click on the settings cog, and you can change the attributes of all your components. Change the resistor symbol. There's a duplicate symbol so that you can get more resistors than that quickly. So you'll be given a certain specification or a certain circuit to use for your Schmitt trigger. This is just an arbitrary circuit to show you how to make them. Going to include a triangular voltage, and what we should get at the output of the op-amp is a square wave. Going to change that to a 4-volt supply. The Schmitt trigger is a comparator, and it will give us 2 threshold voltages which we set by R1 and R2. But for the op-amp, I'm going to change the saturation voltages, the highest and the lowest that it can output, to plus and minus 5 volts. So it cannot swing any more than that. And I've got a 5-volt triangular wave input. I'm going to change that to 10 volts, and I'm going to offset it by minus 5, so the voltage of the triangle wave will go between minus 5 and plus 5. And I'm going to change the period of the triangle wave to 1 second, and I'm going to make the fall time half a second, as in 500 milliseconds, so you put 500 M. So then we have a symmetrical triangle wave. Going to add a voltage probe at the input to look at what we're putting in, call that V in. Voltage probe at the output, which we'll call V out. Then I'll simulate. Click on Grapher, pause it, scroll down as usual, click Zoom All, and that's shown us 19 seconds worth, but you can change the amount of time you're looking at to zoom in. I've put 4 seconds. The period is 1 second. So that shows the output voltage and the input voltage. The blue squarish one is the output voltage, which goes to about plus and minus 5 volts as we expected from the op-amp. The input voltage in green is a nice symmetrical triangle wave which goes between plus and minus 5 volts, as we'd also set in the triangle wave settings. If you press split, it shows you the grapher and the schematic, and then when you click stop you can move the windows. So that should cover various op-amp circuits that you can use for Unit 35. Don't forget to save your file. So hopefully that's been quite helpful to you, and don't forget you can build them on breadboards too.